Okay, so we're going to look at rational functions today, and they're basically functions that involve fractions. So when we have fractions, we're going to have situations where your answer will be undefined when the denominator is equal to 0, because we know we can't divide by 0. So that's going to show us where we're going to have a thing called vertical asymptotes. Hopefully you can remember looking at that before. We'll also have horizontal asymptotes, and a new concept for us is looking at a thing called oblique asymptotes, and that's when they're not horizontal or vertical, but they could be diagonal. Okay, so the types of rational functions we are going to consider are here. Okay, we're going to start with the basic constant over a linear, so a nice reciprocal function like, how about 1 over x? Right, we remember, what does that look like? So let's just go to our graphics calculator, type in 1 over x and have a look. No, didn't select it. Okay, so we select and we have a graph, and we see, or familiar hopefully, the two arcs. Okay, and let's just have a little bit of a closer look there. As x is getting bigger and bigger and bigger, right, we're saying 1 divided by like 100. So 1 divided by 100 is a very small number, so that's why it's getting larger and larger and larger as x gets bigger. As x gets bigger, the value for y is getting smaller and smaller because you're dividing by a large value, but it's still going to be positive. So it gets really, really close to 0, but it won't actually ever touch the x-axis. And what's happening closer to your y-axis? So imagine you're getting closer to 0, but not quite. So something really small like 0.001. So if we're looking at that, 1 divided by 0.01, well, that's 100, right? So when we're getting closer and closer to 0 here for our x value, right, getting closer, the y value gets bigger and bigger and bigger and goes up to infinity. Similarly, on the negative side, as x gets larger negative, you're dividing something small by something big negative, so you get a very small negative answer. So that's why it looks a bit like that. Okay, as we make the value up top larger. Okay, what does that look like? Got to remember to select it. Right, it goes out a bit, and we can make that even bigger. Try 8 over x. All right, keeps going further and further out. I think you know what's coming, that what happens if it's negative, so negative 4 over x, what's going to go on to? Did it again, right? Select, it's going to go into the other quadrants. So that's just familiarizing ourselves with our rational functions of just a constant over x. Now we can take that a step further, and we've still got a constant up top, but now underneath the denominator, it's now not just x, it's x plus 4. We can easily see that our vertical asymptote will occur when the denominator is equal to 0, so that's going to be x equals minus 4. Your horizontal asymptote is still going to be, right, it will always be y equals 0 when you've got a small divided by something bigger, potentially, to get bigger. All right, so if we want to graph this, we're going to, this does not have to be to scale, but because my vertical asymptote is of minus 4, right, I'm shifting that a little bit to the left. So we've got x equals minus 4. Okay, write that nicely. Some other handy things to help you sketch a graph is also your x and your y intercepts. So if we look at y-intercept, okay, really simple. Your y-intercept occurs when x is 0, so that's going to be 2 over 4, commonly known as a half. Okay, so we might pop that over there, 0 or half. Now your x-intercept when y is 0, so we're solving 0 equals 2 over x plus 4. How do we solve this? Get rid of the divide by x plus 4, we times, and anything times 0 is clearly 0. Oops, so we're left with 0 equals 2, which is impossible, so therefore no x-intercept. Now, of course, you could get all of this just from your graphics calculator, but it's nice to sort of know. So we're going to draw our arc, and we'll take a nice smooth curve. So my pen is breaking up a little bit, so sorry about that. All right, so we take a smooth curve, making sure not to cut the x-axis. And then we do the same over this side, not to cut. So it doesn't have to be to scale, but try and make a little bit of an effort. So don't let your graph touch the x-axis or your asymptote. I was getting a little bit close there, so be careful. And again, it doesn't have to be to scale, but try and make these sort of the similar distance away from each other from the corner there. All right, you don't want to be drawing this out here. That wouldn't be a very great graph. Okay, so we'll do another one looking at the next type of function when we've got linear on linear. Okay, so now we're going to look at linear on a linear. Sometimes the question might ask you to put this in the form like y equals, use a different one, e plus something over cx plus d, right? And the reason that they want you to do it like that is because this will be your horizontal asymptote. However, a little bit of an overkill, because as you can see, you can actually get your horizontal asymptote just by dividing your coefficients of your leading term. Now that is also the case when we have a quad on a quad, right? So if I have y equals 3x squared plus da 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 all over 2x squared plus blah blah blah, my horizontal asymptote for that would actually be y equals 3 on 2. Right, so linear and the quads are sort of connected. Obviously, if we've got a quadratic at the denominator, and we'll look at this one shortly, I'm not just going to have one vertical asymptote. I could have 0, 1, or 2. So things do change a little bit there, but when you've got the same degree divided by each other, you can just divide the leading coefficients, and that gives you your horizontal asymptote. But as we said, if they're asking you to put it in that form, remember we can do a couple of things, and you'll definitely have to do this, perform division, when we've got quad on linear or cubic on quad. So when we look at this, I can see straight away my vertical asymptote is going to be x equals 2, because that's what makes the denominator equal to 0. My horizontal asymptote is going to be y equals 3. Okay, if they wanted confirmation of that, remember we've got our good old friend. Okay, 3, 4, and because it's x take 2, that means 2 is our 0, 0, 3, 2 3s are 6. Right, so this can also be written as 3 plus 10 over x take 2. Okay, and of course they've put it in that form because there's your horizontal asymptote. When you're looking at some of the examples that I've popped up there is an alternative, and we can say, right, we look at our denominator, which is x take 2, and we say 3 times x take 2, because we want to end up being able to split and cancel these out. However, if I expand this, I get 3x take 6. That isn't the same as my plus 4. So what do I have to do to make it plus 4? Well, obviously I need to plus 10. Okay, so if I do this, I get 3x plus 4. Do we agree? Hopefully you've said yes. So that's why I pop a plus 10 there. Get rid of all the white noise. Right, and of course if I now simplify this, so ignore the axes, I'm just sort of setting up for the next bit, all over x take 2, which is the same as plus 10 over x take 2, right, cancel, cancel, and I get this thing here. So got to say, for that, I'm probably a fan of simple synthetic division. Anyway, just saying, because you might see that in some books and examples, how do they get it? That's why. But I don't need to write it in this form, because I can just see right here, it's 3 over 1. Okay, here we go. We pop in our vertical asymptote at x equals 2. We pop in our horizontal asymptote. You will be using a ruler, please, at y equals 3. Y-intercept, 4 over minus 2, so our y-intercept is going to be at negative 2. But again, use your graphics calculator by all means to find this out. X-intercept, you make y equals 0, so we're solving 0 equals 3x plus 4. I don't even need to write the divide by x take 2, because to get rid of a divide by x take 2 are times, and 0 times anything is 0. So we get here that this would be x equals minus 4 over 3. Okay, so what does that mean for us? Okay, so we confirm here, it's going to look a little bit like that. So always confirm before you go to just graph it. So we're going to go roughly, oops, that's not great. Roughly like that, and heading towards your asymptote. So that's going to be your minus 2, this is your minus 4 over 3, and then we try and sort of do similarly up here. Now that's where you have to make sure that you've got enough space, and I'm probably just within the margin. Okay, what you don't want is axes like this, draw your asymptote, we've got this, and then you've just got a little tweak up the top. That's no good. Okay. Don't want to keep the video too long, but some of the extra bits that they might ask you to talk about, and that is if they say, can you discuss the graph or describe its relationship, describe the graph as it approaches its asymptotes or near the asymptotes. So you're just saying what you see, but in mathematics. So as x tends to infinity, in other words, as x is getting bigger and bigger and bigger, what's the graph approaching? What y value is it approaching? And we'd say it's approaching this 3, right? And it's coming from above. So you can either put above or you could put a plus there. As x is approaching negative infinity, so as x is going out this way, the graph is approaching 3 from below, or you could put negative. Okay? As x is approaching this value here, right, which is 2, as it is approaching 2, from the right. So from the right, then y is approaching infinity. And as x, right, as we're getting closer and closer this way, as it's approaching 2 from the left, y is approaching negative infinity, right? This is going down, down, down. It's not always going to ask you to do that, but just make sure you read the question. So we'll have a part 2 video where we look at quad on linear and quad on quad.